Experimental determination of the Rates law. In this example, we determine the Rates law for the following reaction using the initial rate data, where the initial rate is the instantaneous rate at the beginning of the reaction. First, we come up with a general rate law. Let rate be equal to the rate constant K times fluorine concentration raised to the power X times chlorine dioxide concentration raised to the power Y, where X equals order of reaction with respect to fluorine concentration and Y equals order of reaction with respect to chlorine dioxide concentration. We need to find the values of X and Y, but how? There are two ways. The first way, we create a ratio of two rate equations of two experiments. But which two experiments? At a glance, when we compare the data of experiments 1 and 3, we notice that chlorine dioxide concentration is the same, or constant, but fluorine concentration changes from 0.10 molar to 0.20 molar, that is, the concentration doubles, and the initial rate changes from 1.2 times 10 to the power of negative 3 to 2.4 times 10 to the power of negative 3, that is, the rate doubles. Since chlorine dioxide concentration is constant, while fluorine concentration and rate change, it is convenient to use data from experiments 1 and 3. Why convenient? We will see shortly. We take the ratio of the rate equation for experiment 3 to the rate equation for experiment 1. That is, rate of experiment 3 divided by rate of experiment 1 is equal to rate constant times fluorine concentration for experiment 3 raised to power X times chlorine dioxide concentration for experiment 3 raised to power Y divided by rate constant times fluorine concentration for experiment 1 raised to power X times chlorine dioxide concentration for experiment 1 raised to power Y. Then we substitute the data, that is, fluorine concentrations, chlorine dioxide concentrations, and initial rates of experiments 1 and 3 into this ratio of rate equation. Data from experiments 1 and 3 are deliberately picked since the chlorine dioxide concentration of 0.010 molar is identical in both experiments. This is good since upon substituting these into the numerator and denominator of the ratio of rate equations, 0.010 molar raised to the power of Y may be cancelled off. The rate constant K appearing in both the numerator and denominator may also be cancelled off. Simplifying further, we cancel off 10 to the power of negative 3 from the numerator and denominator on the left-hand side of the equation. 2.4 divided by 1.2 is 2. On the right-hand side of the equation, since the numerator and denominator have the same power of x, we can enclose 0.20 divided by 0.10 within brackets and raise this to the power of x. We tackle division first. 0.20 divided by 0.10 is 2. Thus, we get 2 to the power of x. 2 equals 2 to the power of x. When a power is omitted, it is because it is understood to be 1. Therefore, x equals 1, which translates into the reaction being first order with respect to fluorine concentration. Next, substitute this value of x into the rate law. If the power is 1, showing the power 1 is optional. So we have rate is K times fluorine concentration times chlorine dioxide concentration raised to power Y. We now have to solve for Y. We do something similar. We come up with another equation by taking the ratio of two rate equations involving the data of another two experiments. This time around, we use data from experiments 2 and 1. We apply the same trick of cancelling off the same fluorine concentration of 0.10 molar raised to power x rate constant K, as well as 10 to the power of -3 from the numerator and denominator. 4.8 divided by 1.2 is 4. 0.040 and 0.010 share the same power of y. So we enclose 0.040 divided by 0.010 within brackets, then raise this to the power of y. We get 4 to the power of y. 4 equals 4 to the power of y. Once again, y must be 1. Therefore, the reaction is also first order with respect to chlorine dioxide concentration. Now we have the complete rate law. It is rate equals K times fluorine concentration times chlorine dioxide concentration. Showing the power of 1 is optional. Now for the second method for obtaining the rate law, the inspection method. Earlier, by comparing data for experiments 1 and 3, we noticed that chlorine dioxide concentration is the same, or constant. Going from experiment 1 to experiment 3, fluorine concentration doubles and the initial rate also doubles. So when the fluorine concentration is multiplied by a factor of 2, we notice that the rate is also multiplied by the same factor of 2. It is the same proportionate increase. Thus, x is equal to 1. The reaction must be first order with respect to fluorine concentration. To find x by this method, the chlorine dioxide concentration must be constant. Then we can say that any change in the rate is due to the change in fluorine concentration, not due to chlorine dioxide concentration. Next, we have to find y. By comparing data for experiments 1 and 2, we notice that fluorine concentration is the same or constant. Going from experiment 1 to experiment 2, chlorine dioxide concentration quadruples, and the initial rate also quadruples. So when the chlorine dioxide concentration is multiplied by a factor, in this case a factor of 4, the rate is also multiplied by the same factor of 4. It is the same type of proportionate increase. Therefore, y is equal to 1 and the reaction must be first order with respect to chlorine dioxide concentration. Using this second method, we also arrive at the same rate law. That is, rate equals K times fluorine concentration times chlorine dioxide concentration.